Hello, Kirtana, I'm audible.
Yes, sir.
Okay, so in the last class, we were doing about magnetic moment, right? Or you can say magnetic dipole moment. So we solved some problem, and yeah, at the end, I gave you one relation that magnetic dipole moment divided by the angular momentum will result to what? The charge divided by total mass, right? This is what we resulted in the last class. Could you remember that?
Yes, sir.
Okay. So here, what if, look, if you could remember, the last problem we solved was I gave you a single ring, right? I gave you a ring which is rotating about this axis with speed omega, right? So I asked you to calculate magnetic moment in that case. The charge was Q and mass was M, right? So again, we solved by using a rough integration method also, and I gave you this method that dipole moment divided by angular moment results to Q by 2. So with that way, what is this? This is nothing but Q by 2m. What's the angular momentum of a rotating ring? That is nothing but moment of inertia multiplied by the omega. So here, if you could remember, this I comes out as how much? Okay, okay, fine. Yeah, and what is the angular momentum of a rotating object? Rotating ring basically, right? Because all the mass is situated outside of the body. You can call this as mr square and the omega as it is. If you want, we can actually substitute the value of omega also. Otherwise, we can just let it be. For example, cancel 2 r square omega. This is the answer we got, right? Is this clear?
Yes, sir.
Okay. Now, I'm extending this problem to a such state that instead of a ring, you are given a disk now. Okay. This is a disk given to you. About this point, this disk is rotating with omega. Okay. Now you need to find out magnetic moment. Okay. So you need to find out it. Can you calculate this? It's very easy. If you could, if you just go with the main concept which we have studied so far, this is very easy. This problem. Instead of ring, I have given you the disk. So just solve it and get me the answer first. Kirtan, solve it fast and let me know the answer. Look, this problem is easy. Okay, so I'm not expecting you to invest a lot of time. Okay.
Sir, is it you ask Ramita the first?
What's the answer?
You ask Ramita.
Look, your voice, I don't know why it's lag in between.
You are square omega by 4.
Yeah, exactly, it's 4. Okay, so how did you solve this case now?
Momentum is equals to q by 2m into inertia into omega.
Exactly.
That's it.
Basically, yeah, makes sense. This you can use this method also, and you can actually go with another method also. Okay, so it's your call. Yeah. What can be the another method, Kirtana, to solve this? If I ask you, let's not use this method. You can you solve it using some other method? Don't solve it. Just let me know. Okay. You don't have to solve with other method. You just have to let me know the thing. Like, do we really have any other method to solve it, or
Integration.
exactly the integration? How you are going to do the integration for this one? What is the main key component which you are going to integrate? Okay, look here now. So yeah,
That
uh, look, we already know what is the magnetic momentum due to this ring, this part, right? This is single ring. So what in this disk we are going to do is, I will take from this center, I will go at some distance x, I will cut out a small strip of a ring. Okay? I will say I already know what is magnetic moment due to this ring, right? Then I will say let's do one thing. Whatever the magnetic moment I'm getting, let's say this is the magnetic moment you are getting something. Okay, I don't know what is the value you are getting. In some form, let's say f some x. In some form of f dx you are going to get. Okay, this is function of magnetic moment due to this. So what you are going to do, you just integrate it from 0 to x. Right? That will result to the final answer of this thing. Because when you integrate this, you'll get this m is equals to 0 to x. Some function of this dx and some constant outside, because it is not necessary that all the things gets inside itself. Okay, so some function of this thing you have to take. Clear? Understood? I'm not writing the whole function. So yeah, you know that function will be kind of this, right? Q x square divided omega by 2, and this q will not be the complete q. This will be some half portion of the q, right? Some very small portion of the q. That's what the answer is. So yeah, these are some concepts we have to study. By another simple m by L method, if you go, q by 2m you can put, m comes out as q by 2m. L is basically I omega, so I is in this case half mr square, because this is a moment of inertia of a disk, which is half of the total thing multiplied by the omega. So you got the answer is q omega square by, that's what the answer is. Makes sense. Now we can move to the next. But in this case, I'll take the similar thing, but the shape will be different. Okay. In this case, the shape comes out as a hollow sphere. You are given a hollow sphere. Okay? Some kind of hollow sphere is given to you. Okay. So this is basically a hollow sphere given to you. Um, how we can let it rotate? Assume about this axis. Let's say about this axis, this central axis, it is rotating with speed omega. It is rotating with speed omega. You need to figure out the angular momentum. Okay, you need to figure out the magnetic moment. Find out magnetic moment of. Yeah, so you can try it once and let me know the answer for this one.
Sir, is it Q by 3 R square omega?
Yeah. What's the answer you got, Kirtana?
Q R square omega by 3, sir.
Exactly. Okay, that makes sense. So yes, this is what the answer you're getting over here. Makes sense. But okay, this method is actually correct. But can you also solve this using integration method? I just wanted to know what kind of component you are going to take in this also. Okay, so you could know that this method is working very good. Simply apply m by l is equal to q by 2m. That will result in the answer. Okay? This is working very well for you. But here, my question is, what kind of component you need to take? What kind of small element you are going to take for this sphere? If I say don't use this direct method, use a whole integration method. Because look, right now, whatever the shapes I have given you, these are very symmetrical around, and we also have a direct formula for that angular momentum. Yeah, angular momentum, right? What if I give you a very random shape, right? In that case, you should be very well aware with the integration method as well. So yes, which kind of component you are going to take in this picture? Okay, let's leave it now. In this case question, I'm twisting the problem now. I'm saying instead of calculating magnetic dipole moment, can you calculate magnetic field at the center point, very center of the circle, center of the sphere? Can you calculate the magnetic field at the center?
Yes.
Here I'm asking magnetic field. Okay. Just think of it how you are going to calculate magnetic field over here. Okay, I'll actually simplify this figure a little bit. Okay. Just remember this is the axis about which, about which it is rotating. Okay, this is the axis. Yeah, good. Now, could you think of it any ways like how we can actually solve this problem? Okay, should I give the solution?
Yes.
Okay, look. All right. Now, instead of this problem, if I ask you, can you calculate magnetic field due to this ring? This ring, okay, it is rotating about this axis with omega. Can you calculate magnetic field at this point at some distance x?
Yes.
Okay, how you are going to do that? Just explain to us. You don't need to solve it. You just have to explain it.
From the point that we need to calculate the magnetic fields
No, I know.
integrated.
Yeah, that makes sense. What you are going to integrate
uh, dB is equals to u naught I by 4 pi into dl into r by r.
makes sense. So basically, okay. But if you see, I have not given you current over here. So why there will be magnetic field at this point? Why even we are talking about magnetic field, even though you can see there is no current in the circuit, or there is current, because we have seen magnetic field is produced due to mu naught I, right? So where is this I factor in this? Could you explain about this current part also? Why even we are talking about this? Because to have magnetic field, you must have something current over there, right? Either there should be an existing magnetic field or you have to produce. So how we are going to produce magnetic field over here? To produce magnetic field, I need current. Can you see something which can provide it current? Remember once, this is non-conducting, okay? So just think of it once and let me know the answer.
Is it due to omega's
Is it due to
rotation? Due to the rotation.
okay, due to what?
Rotations.
Yeah, exactly. Okay. So basically, this rotation is providing you the angular what? Okay. Why even this rotation providing that thing? Why we are getting current due to rotation? Why you are confused this much? We have already studied this thing earlier, right? That a rotating ring provides current, or any rotating objects have current, right? Why there is current? Look, let me see. This is an object. It is rotating. So, with respect to my frame, can assume that I'm giving a circle over here, right? And it starts rotating with this frame, and I'm sitting in this like this way. Will you even notice a change if this ring is a uniform ring? Like at each point the color is same. Would you even notice that ring is rotating? No. It means I will see that ring is on a stop, but internally ring is rotating. Ring is rotating. What does this mean? The electron which was placed here after some time will be here because it is rotating. The electron which was here will reach here, right? Or you can say the electron which is here, it will reach here. This electron is going to reach here. This is going to reach here, and so on. It means electron is moving. If electron is rotating in this way, current is going to be in this way, right? So that's how we are talking about current. Okay, we are talking about current. How current is over there? Yes, it is actually there. So how much current will be there? Current is nothing but Q by T, right? Okay, how much current is rotating? You can see if I talk about the complete run, right? In one revolution, the electron which is present here will take t time. Basically, after one revolution, it will reach here back. It means all the electrons in one revolution will take complete circle, right? It means what is the time? What is the time to reach back to their own position? That is one revolution. I can call that as omega by 2 pi. Sorry, it is 2 pi by omega. We have done this thing earlier. It's 2 pi by omega. This omega reaches to the top. This is the current. Okay, this is the current you are supposed to have. This makes sense. So now how we are going to solve the above problems? We got the current value also due to a ring. Okay? So for that I'll write over here. Let's see. Current due to ring rotating with omega. What is that? I is equals to q omega by 2 pi. Okay. Charge should be there should be some charge. So now how we are going to do this? Look here now. Can I do one thing? From this center point, I will go and reach some outer point this at some angle theta also. I am going to take some d theta position. From here you are going to take d theta. D theta means to say this will look like this, and this. It will be a complete circle from that side also. So how this thing looks like, if I make it over here, it looks like this. This is the center point. Okay. This is the one circle you have taken out, and this portion of a circle. Okay, this is what we have taken out. Because and this is basically, this is going to be very small width. Okay. This width, if you talk about, this is dx very small. So when the thing is very small, it will feel like a ring itself. Okay. So this will be from that side also. This kind of thing you are going to observe. Understood? Is this clear, Kate? Now, what you are actually calculating? You are calculating at this theta, right? Can I say you are basically calculating? Okay, one more thing. If it is rotating in this way, what is the direction of current you are going to get? Look, it is rotating in this way, right? It means electrons are moving this way. It means current is in this way. Current is in this direction, right? If current is in this direction, right? If current is in this way, due to this ring, if I talk about this point, what is the direction of magnetic field you are going to get? Perpendicular to it. This is the direction. Okay, makes sense. Now, if I say you reach some angle theta, you took d theta carved out. It means if this is theta, I can simply say this is 90 minus theta. Sorry, I'll just try to extend it once. So this also becomes theta. Okay, the whole is 90 degree. This becomes how much? This is 90 minus theta. 90 minus theta. This is what. Now you can simply say, sir, the perpendicular component is going to come out as b times of cos theta, and this component is going to be b times of sin theta. This is what you are doing. Clear? Understood?
Yes.
Okay. If you say this is rotating in opposite direction, maybe like this. So if it is rotating in this way, then your current will be downside like this. In that case, your magnetic field will be like this. Just like this. Magnetic field is going to be this way. Okay. If this is angle theta, this will, yeah, this whole, yeah, this is also theta. This is 90, 90 minus, this will become theta. So you can say this component, sorry, wait, uh, from where we are taking this component. Okay, makes sense actually. This theta we have to take it like this, right? Okay. So this will again come out as, what is that? The current is in this direction. So with this way, the magnetic field is downside. Yeah, if this is theta, this is 90 minus, this will become theta. So this becomes 90 minus theta. So this becomes b of cos theta, and inside you are going to get b of sin theta. This is what at the end of the day. So Kirtana, can I say if you do a complete circle, this perpendicular component is going to get cancelled out, and we have already seen this thing, right? When we were calculating a magnetic field due to a ring carrying current, we have already seen that the value what we get in this case. We have already calculated it in the earlier classes. What was the value? The value was B is equals to mu naught, right? What is the value? Mu naught n I r squared divided by 2 pi, sorry, 2 times of x squared plus r squared. This was the magnitude we used to get. This is the magnetic field value due to a ring at some distance x, right? So this is also acting as a disk. So can I say here, because this is a small component, so this will be dV itself. Can I use that? Can I use this formula written over here?
Yes.
Okay, so we are going to use that directly now. So let's remove it once. Now I'm going to say that magnetic field dB will come out as how much? Uh, mu naught, right? Current is how much? What is the current value? We already know this is going to be a current. Okay, we are going to put the value later on. Now just keep it as this. Okay, what is the distance? If you see, this is radius r. Okay, this is radius r. This is angle theta. So what is the distance? That is r times the cos of theta. Okay, so in this case, the when the formula says that mu naught okay, mu naught I r square basically. Here my r square is r times of cos of theta times of square divided by 2 times of r cos theta square plus perpendicular, right? This here radius of the circle. In this case, the radius of circle is r of sine theta. R of sine square theta times of 3 by 2. This is the answer we are getting just with dv. So mu naught I r cos square theta divided by. If you see carefully, it is cos square theta sine square theta. R square will come out common. So what is the final thing you are going to get? R square, because there is a 3 by 2 and this thing is into 1. So this is what we are doing. Is it clear, Kate? Once?
Yes, sir.
Okay. So this r square and r square get cancelled. What we have got finally? We will actually write all the simplified equations. Okay, let it be as it is. It is going to be mu naught I cos square theta by. This is the magnetic field you are going to get in this particular case. So now Kirtana, you have got this value, right? What is the value of I? We can substitute it. But here dq. What is the dq? Total charge on this is q. So what is the charge on this smaller portion? I can do one thing. I know this is a hollow sphere, right? But I can say this charge is spread over 4 pi r square. Is it? Can I say on this ring the charge is spread over the smaller area? What is the smaller area? You can say, sir, I don't know the smaller area, but whatever the d theta, what basically this is if you cut it and open it, how it will look like? This dx length and this total length. What is the total length? That is parameter. So what is the parameter over here? 2 pi r. In this case, the r of sine theta is the radius multiplied by dx. But what is dx again? When you cut it in this way, this was d theta. So what is the dx? Dx is nothing but r times of d of theta. Okay, this is the answer. So instead of this, you can substitute in this way. Go and substitute it. So you got r times of theta. Clear, Krishna?
Yes.
This is d theta. Okay, so this is 2 pi r sine theta r times of d theta. This is the area of this is composition. What is the dt you have got? You can say 2 cancel, 1 r to 1 r cancel, this 2 so this 2 cancel. So dq comes out as q sine theta. Okay, this r to this r completely cancel out. Okay, dq sine theta, I think d theta divided by, this is the value you are going to get. Clear? I think so, yes. So we can actually go and put the value. So what is the current over here? You can just see multiplied with omega divided by 2m. So you will get the I. Okay, I'm going to put the direct value. dV is equals to mu naught by 2 constant, all the constant outside. Put value of this I. What is that I? Q omega by 2. So omega by 2m also constant. So instead of 2, I'll write it as 2. Okay, let it be 2m. 2m as it is. What is the value of I? So omega kept, 2m kept. What is the value of q? This is the value of q, dq in this case, right? Q sine of theta divided by 2. And instead of d theta, I'll write later on. First, let's give this cos square theta. And what is that? D. So mu naught. Okay, let's write the whole equation once. 2, 2, 4, 8, and here you are having q. So you can see you just need to integrate this small portion. Also, this is cos square theta. It can be written as 1 minus sine square theta, and this is d theta. D. Clear? When you integrate it from 0 to complete. Yeah, clear. So is this part clear?
Yes.
Okay, makes sense. Now, what we can further rewrite over here is mm, cos square theta, and in the key part of this. Just a second, let me see if something mistaken again so far. I don't think so. Okay, here we are getting cos theta as. Okay, Kirtna, this is one mistake we have done. It should be sine square theta. Why this is sine square theta? Because in general, the formula, what is the formula? That is B is equals to mu naught I r square divided by 2 times of r square plus x square. Okay? Here, this 2r cos theta is x and r sin theta is r. So here it should have, we actually it should not be like this. It should be sine of it. So let's put it sine r times of sine. So this will become sine itself. We don't even have anything as cos, and this will again go as sine. So you can actually see we are getting something like sine cube. Clear? So here, if look now, what I wanted to do is I can't directly integrate this sine cube theta. Okay? So what you can do is split it into two. So say sine theta, sine square theta. Now write that sine square theta as cos square theta. Okay? One minus cos square theta. So it will come out like this. Now the rest part is integration. Okay? Can you do the integration of this part, or I have to solve this? Okay, let's take this at this small portion. Do one thing. Put the 1 minus cos square theta as t. Okay, so t is equals to 1 minus cos square theta. Okay, I'll do this using some different color. T is equals to 1 minus cos square theta. Differentiate the whole thing with respect to t. The moment you do so, you are going to be dt by d theta is equals to minus. mm, is it? Oh no! Don't do this. Do one thing instead of this. Put this equals to cos theta. Okay? Put this equals to cos. Now differentiate. The moment you do this, d theta by dt will result to minus sine theta. Minus sine theta, and you can put d theta is equals to minus sine theta d theta is equals to negative. Okay. So you can see I have sine theta also, I have d theta. Instead of this, I can put minus d theta. So this will result to b. This is complete integration b. Here mu naught, it is mu naught omega omega q by 8n. Okay, this integration results as 1 minus cos theta we already kept as t, so it will result to t square, and here it is dt. And there's a negative at the front because there was a negative associated with it. Now you have to integrate it from where to where you are. Look, you have to cover the whole thing, so you need to integrate it from angle 0 to complete 180 degree. Okay? 0 to minus 180 degree. So just go and keep the values. 0 to minus 180 degree. You have two ways. Okay, don't put this value in t. Okay, so here I am not changing the limits. For example, these limits are still with respect to the theta. So after putting the value of t in form of cos theta, we are going to put the limit. Or if you want to keep directly the limit of t, so in that case you need to substitute the limit. Okay, how we can see that also cos theta is equals to t, right? So when theta is 0, because we are going from 0 to 180 degrees, so mm, okay, let's do one thing. Let's integrate this thing also from here to the top value. Okay, let's integrate it once. We'll see after that. Okay. So the moment you go and do this, what you can see at 0 cos theta 0 comes out as cos 0 comes out as 1. right? And cos 180 comes out as minus 1. It means when you are putting theta as 0, like you are going from 0 degree to 180, right? Instead of this, you have directly changed the thing, right? So what is the limit you are going to get for the t also? That will go from minus 1. So, because you are going to put the direct value, right? So it will go from 1 to minus 1. Either do this way, either put the value. So here, instead of this, you can directly write it 1 to minus 1. So b negative mu naught omega q by 8m. This is t minus t cube divided by what is that? 3. Okay. Now put the value. The moment you put the value, what you are going to get? Initial is okay. This is actually bigger value. So yeah, great. Now look, magnetic field comes out as multiply inside mu naught omega q divided by 2 8 times of m t cube minus t by 3. Limit is 0 to sorry 1 to minus 1. Either if you want to keep cos theta value, then after that you have to keep a 0 to 180. But I have converted it, so it will be like this itself. Mu naught omega q by 8 m. So what it will be? Put minus 1 first of it. So that will be minus 1 minus 1, that will be minus 1 6 by 3. Here it will become plus 3 plus 1. Subtract. We have to subtract this part, so put this 1 by 3 minus 1 plus 1. This is what you are doing. Yeah. Yes, I think so. So what you see over here is the whole thing comes out as mu naught omega q by 8m. Okay, two times of the whole thing. So the resultant of this comes out as 2 by 3. So it will become 4 by the whole thing. So what is the final answer? Omega mu naught mu q by this 4 to 2. So 2 into 6. It will give it 6. This is the current value you are going to get. Okay. So this is the answer you are going to get here. Any doubt till here?
No,
No doubt, right? Okay, let me see why there is n value over here. And we've got substitute somewhere. This mass should not be in the part of this. dB we are getting is omega by 2m. Okay, wait. Why it is? Okay, sorry. This is pi, not omega. Okay, this is the mistake we did. It was pi, right? Because pi is nothing but q by time, and time is nothing but 2 pi by m. So 2 pi by omega. So omega goes to the top. So instead of this m, you have to substitute. Let's substitute the everything. Wherever the n is written, keep it as pi. So here and first time is written somewhere else. I can't see here, here, here. Anywhere else m is written, you can see. I don't think so. So pi, pi, and at here it will become m. So pi, pi. At the end, this will be pi, pi, pi. At the last, 8 pi. So 6 times of pi. This is the answer we have got here. Any doubt?
no.
Any doubt? No doubt, right? Okay, let me see if any mistake has been done. I don't think so. There should be one R also. Don't know where it is. From here, we cancel out both of the R's. So, yes. Okay. Make it square. Here is sign. Okay. R, R. And from where we are not getting this R value. Okay, okay, sorry. Here use cube because your R square outside 3 by 2 that results out R cube. So 2 cancel out the top, 1 at bottom. So 1 R should also be there. So here it is cube, cancel. R should be here. R should be here. In red and white, R. R. In final, it should be R. Look, this problem is bit lengthy, so you have to check it once. Okay. So yeah, Ketan, that's all for the today's session. I will end it by this. If you haven't doubt, please let me know.
No, that's
No doubt. Okay, I'll give you one task. Here. What we started, you are given a hollow square. I okay from this axis I took one small element as a ring, so we already know the value of a magnetic field due to a ring at some distance x. So we directly apply the formula. Then we converted the things and later on we just integrated the part. So this is what the procedure is. By this, we are done with this complete topic. In the next part, we'll start with magnetic induction. Okay? After doing magnetic induction, we will do what I can say, alternating current part, and then E and the. This is all about syllabus we are going to. So yeah, Kirna, that's all for the today's session. I'll end the session by this. If you have any doubt, please let me know.